Module 5, Introduction to Probability. What does probability have to do with statistics? Well, probability is what will enable us to determine how well a random sample reflects the larger population about which we want to make inferences. So probability gives us a way to quantify uncertainty, and precisely, it's the likelihood that something will happen. So we have some notation that we'll be using that you should be familiar with. Suppose A is an event or an occurrence. Then the probability of event A will be denoted by P for probability, and then in parentheses we'll put event A. And notice we're using all caps here. If an event is impossible, then the probability of the event is equal to 0. If an event is guaranteed to happen, then the probability of the event is equal to 1. So a first rule that you need to keep in mind, for any event A, we're going to have that the probability of event A will lie between the numbers 0 and 1. They'll never be outside of that range. So an example, just to kind of solidify this, what is the probability of pigs flying? As far as we know, it's 0 right now. What is the probability that your height will increase by 3 inches overnight? That is not going to happen, so that probability is 0. What is the probability your Social Security number will be the same tomorrow? For most of us, that's certain. Haven't gone through any changes, so that would be a 1, meaning it's definitely going to be the same. And what is the probability that it will rain in Seattle at least once during the month of April? Well, Seattle is known for being rainy, so that's highly probable. So we would say that that's equal to 1. Okay. The next example, circle the appropriate description of the probability of each event. What is the probability of winning over $1 million in a state lottery? Well, that value, we know it's not impossible because somebody does win usually. So will the probability be close to 0 or will it be close to 1? Well, unfortunately, it's not likely, so that probability will be close to 0. What is the probability of passing your CJC objective assessment? Well, we are all very hopeful, and the fact that you're watching this video means you're putting in the work that you need to study. So I would say you have a good likelihood of passing the assessment. So we would say close to 1. So as we know, every event is not certain. So we need to learn how we can compute probabilities that are not going to lie at the extremes of 0 and 1. So before we do that, let's define a couple of types of probability. The first type of probability is determined by the nature of the event, and that's a theoretical probability. The second type of probability is determined by observing the outcome of a series of trials, and that's called an empirical probability. We can use a series of empirical probabilities where we're looking at the outcome of trials. So we're doing a bunch of experiments, observing the outcomes. So we can look at that series of experiments to determine the theoretical probability. Okay, another definition, the relative frequency of an event A is equal to the number of times event A is observed. Okay, so the number of times A is observed divided by the total number of trials. just clean that up a little bit. So in a series of experiments, the relative frequency of event A is the number of times A is observed divided by the total number of trials. This value can be used to approximate the probability of event A. So let's look at an example of this. Suppose 500 people out of 2,500 surveyed indicated that they watch reality TV shows. What is the probability that one person chosen from the sample watches reality TV shows? Well, this is when we can use the relative frequency of event A. We know that 500 out of 2,500 surveyed watch reality TV shows. So that would be an estimate of our probability for the entire population. So we can simplify this. It's equal to 1/5. So fractions are fine, or if you prefer, you can put it in decimal form. So 0.2. Okay, so for this sample, looks like the likelihood of watching a reality show is not as likely as not watching a reality show. Part B, and the reason I say that is because 0.2 is closer to 0 than it is to 1. Part B, can we assume that the probability that one randomly chosen Georgia resident watches reality TV shows is the same as Part A? So can I assume that the probability is 0.2 that one person from Georgia, randomly chosen, watches reality TV shows, and explain? The answer would be no, because we need more information about this sample. We don't know where the sample was taken, how the participants were gathered. So no, because we need more information about the sample. The sample may not have been representative of everyone in the United States. We're not even told that this was only U.S. citizens surveyed. Okay, moving on to our next example. I want you to determine the following empirical probabilities. So suppose that you flip a fair coin. What is the probability that you would get tails? Well, we know that there are two possibilities, and tails is one of them. So that probability would be 1/2. Well, what is the probability? Suppose you roll a die. What is the probability that you roll a 3? Okay, well, there are 6 possibilities, and there is 3 out of those 6 possibilities. So our empirical probability would be 1/6. What is the probability that we would roll a 1? Again, 1 out of 6. What is the probability that we roll a 7 on that die? That would be 0, because it only goes from 1 to 6. It's impossible to roll a 7. What is the probability that you would roll a number between 1 and 6, inclusive? Well, that's guaranteed. We're definitely going to get a number between 1 and 6. Inclusive means that 1 and 6 are included as well. So that would be a 1, because we'll definitely get a number in that range. Next, we have this important law, the law of large numbers. As the number of repetitions of an experiment measuring a certain event increases, the relative frequency of event A will approach the actual probability of event A. So in other words, when you compute the relative frequency using experiments, the more trials you do, the more times it's repeated, the value that you come up with is going to approach the value of the actual theoretical probability. Okay, so I'm going to leave for you to look at a simulation in the Open Learning resource on page 91, where it simulates flipping a coin. Okay, or you can just use a coin if you prefer. So let's say that you were asked to flip a coin 10 times. How many tails do you get? Okay, so the answers are going to vary here. Okay, so I flipped a coin 10 times and I got 6 tails. So the estimated probability of getting a tail is 6 out of 10, which I can simplify to be 3/5, or if I want to put it as a decimal, 0.6. So out of my 10 coin tosses, which is on the bottom, I ended up with 6 tails. So my estimated probability, using my relative frequency formula, I take the number of times this event happened, which is 6, divided by the total number of trials, 10. Okay, so let's say I take my coin and I flip it 20 times. How many tails do I get? Okay, well, when I did it, I came out with 11 tails. So what is the estimated probability of getting a tail based on this result? Well, I got it 11 times out of 20. So if I approximate that, this is 0.55. So if you flip the coin indefinitely, the result will be the theoretical probability. And when you use this computer simulation, it'll let you do 100 coin flips just at the click of your mouse, or 1,000 coin tosses. So if you flip the coin indefinitely, the result will be a theoretical probability, which is going to be 1/2, or 0.5. So the more tosses, the closer that these numbers are going to get to 0.5, the true value. Okay, well, unfortunately, probability is not always intuitive, as this example will illustrate. So some of you may remember the game show, Let's Make a Deal. It was a game show that had a great prize hidden behind one of the 3 doors. So pick a door that you think the prize is hidden behind. Okay, so I'm going to arbitrarily choose door number 1. Suppose I open one of the doors that you didn't choose and show you that there is no prize behind it. Are your chances of winning better if you change your selection to the other unopened door? Explain. Okay, so let's say that I chose door number 1. What is the probability that I chose correctly? I have a 1/3 chance that the prize is going to be behind that door. However, there's a 2/3 chance that it's going to be behind one of the doors I haven't chosen. So then, if they tell me that the prize is not behind door number 2, so I know that there's a 0 probability, since they showed that to me, that the prize is behind door number 2, that means that this 2/3 chance now rests with door number 3. So I would actually be better off switching my answer, or switching the door to door number 3. So are my chances of winning better? Yes, because there is a 2/3 chance that the prize behind one of the other 2 doors I did not choose. Since I'm told which door it is not behind, that means there is now a 2/3 chance of the prize being behind the door I did not select. So this is one that may not seem logical. Hopefully you followed my reasoning, but this is an example of probability not necessarily being intuitive. Go on to our next page. So the point is, you want to make sure that you use the different rules and laws of probability that you're learning, and that you will learn to answer questions, not just rely on your intuition. Okay, in this example, number 1, I toss a penny and observe whether it lands on heads or tails. Assume the penny is a fair coin. This means, so what does it mean for the penny to be a fair coin? A, every occurrence of a head must be balanced by a tail in one of the next 2 or 3 tosses. Nope, not necessarily. B, if I flip the coin many times, the proportion of heads will be approximately 1/2, and this proportion will tend to get closer and closer to 1/2 as the number of tosses increases. That makes sense. Part C, regardless of the number of flips, half will be heads, half will be tails. That's not true. So D cannot be true. B is the answer we're looking for here. Okay, number 2, a basketball player makes 160 out of 200 free throws. We would estimate the probability that the player makes his next free throw to be, well, this is when we can use our rule by taking the number of times the event occurs divided by the number of trials. So if we do 160 divided by 200, that gives us 0.8. So that's what we would estimate the probability to be that he makes his next free throw using our relative frequency. Number 3, the probability of an outcome of a random phenomenon is the precise degree of randomness present in the phenomenon. B, the proportion of a very long series of repetitions in which the outcome occurs. C, the probability of an outcome of a random phenomenon is either 0 or 1, depending on whether or not the phenomenon can actually occur. Or D, any number as long as it is a value between 0 and 1. The answer is D. We know that the probability can be any number. Actually, it can be any number that's between 0 and 1, although it can also include those values. So let's go back up here. The proportion of a very long series of repetitions in which the outcome occurs. So this is one where it seems like it can be B. I'm going to reject D since we don't say it can also be 0 and 1 inclusive. So B would be our answer here. Okay, number 4, the collection of all possible outcomes of a random phenomenon is called the census, the probability, the sample space, or the distribution. Okay, all possible outcomes is called the sample space. Number 5, I toss a fair die with 6 sides. The probability that I roll a value greater than 3 is, well, we know that that means we can roll a 4, a 5, or a 6. So that's 3 out of 6, or 1/2. So C would be our answer for this one. And our last one, I choose a card at random from a well-shuffled deck of 52 cards with the typical 4 suits. So we have spades, which are black, diamonds, red hearts, and then black clubs. What is the probability that the card chosen is red? Well, half the deck is red. We have 13 hearts, 13 diamonds, so 26 out of 52, which simplifies to 1/2, or 0.5 if you prefer. B, what is the probability that the card chosen is a 7? Well, there's a 7, 1 7 in each of the 4 suits. So that means 4 out of all 52 cards will be 7s. So make sure you simplify. So this will give us 1 out of 13. Part C, what is the probability that the card chosen will be red or black? Well, those are our only two options. The card that I choose is going to be red or it's going to be black. So that's guaranteed. So that probability equals 1. Part D, what is the probability that the card chosen will not be a heart? Well, for it not to be a heart, that means it can be a spade, a diamond, or a club. So if we have 13 of each of those, that means 39 out of 52 of the cards will not be a heart. And this will simplify to be 3/4. And lastly, what is the probability that the card chosen will be blue? Well, we know that we only have black and red, so there's no chance of getting a blue card.